Good morning, 8th graders. I am going to walk through the answers to the Force and Fan Cards Lab. I would like you to follow along and correct your class kick as I go through them. So the first one, your prior knowledge questions that you did before the gizmo. 1. If you are pushing a shopping cart and you start to push harder, what happens? The answer to that, the cart speeds up. 4 words, you guys. The cart speeds up. But something important that not all of us did, even though it's just a short answer, was capitalizing and punctuation. When you write up a science lab, you need to write in full sentences. That means proper English. Please correct your sentences if you are not using proper English with capitals and periods. Question 2. What happens to a shopping cart if you get it rolling and then release it? The answer is that the cart continues rolling, gradually coming to a stop. The reason for the stop is because of friction. If you included that, bonus points to you. Because of Newton's first law, if nothing were ever in the way of that cart, including friction, it would roll forever. But after you push it, the force of you pushing it stops, as well as other forces such as wind resistance or that friction ground resistance, which gradually makes it come to a stop. It's not a screeching halt because it doesn't hit anything and you were originally pushing it. As you move on, you get to the gizmo warm-up. So in the gizmo, you turn the fan force to off and then click play. Did the cart move? No. When you were not putting any force on the cart, of course it did not move. What that looks like is this. Off, playing it, my cart is not moving when the fan is off. My speed on my speedometer, 0 centimeters per second. Doesn't matter if I change the ground. When it is off, nothing is happening. Nada. Click reset. Press the low fan force button to turn the fan on and click play. Low. It moves. So the answer there, it moves. It began moving to the right. However, you write that full sentence that has both a capital and punctuation. Happy with it. A force is something that causes a change in motion. What provided the force that made the cart speed up? Was someone pushing it? Was it a fan? Was it a magical elf? So in this case, the fan provided the force. The speedometer, this little guy over here in this corner, shows the cart's speed or how fast it moves. And then this was what confused everybody. The example they gave us of a speed of 30 centimeters per second means the cart moves 30 centimeters every second. That was just mansplaining something. Okay, it was not necessary. They are asking us what the final speed of the cart was, that we were in metal surface, no objects. So if I reset it, I go metal surface, no objects. We're going to let our cart run. 123.3 is what I ended at. so theirs was a little bit different. Anywhere in there is good. 122.7 centimeters per second, 123.3 centimeters per second. If you played it and you stopped it here, you could tell me 108 centimeters per second in the time of 7.1 seconds. So that one's going to be a little bit different for everybody, assuming what time you stopped it. Question 5. Friction is a force that works against motion as surfaces rub each other. Click reset. Select no friction. Click play. What was the final speed this time? So that's telling us we were on metal. Now do it no friction. See what it's like. (134.3 centimeters per second. Mine's a little different, but pretty close. 134.8 centimeters per second. Get the gizmo ready once again for activity A. You reset, set the surface to wood, be sure there are no objects yet, and fan force to low. Nothing's in my cart. Press play. What is the final speed of the cart? Wow, that's a slow cart. 90.9. 90.6 centimeters per second. So pretty close there to the gizmo answer. Now you predict with the cart's final speed, so that's this here, based on distance and time, would it be higher or lower if the fan was set to medium? Obviously, the final speed would be set higher. This is our only force that's happening, so if I set it to medium, same ground, it is clearly going to move at a faster speed with more force because of Newton's second law. What was that final speed? 119.1, 119. Oops, don't look at that. 0.3. Depends on your settings exactly. Conclusion. Did the cart speed up more quickly with the fan on low or medium? Look at that whole sentence. The cart changed speed more quickly when the fan was set to medium. Fill in the blank. Speed is the answer to both. Force causes the speed of the cart to change. If more force is used, the speed of the cart changes more quickly. Now, the instructions are to select the Data tab. It's here. And then it's up to you whether you want to see a bar graph or a line graph. The graph shows the cart's speed over time. How would the graph be different if the fan were on high? So if we go take a look on it, over time here, we're seeing an increase. 8 seconds, 119, 8 seconds, 119. I wonder how this graph would compare if we took it to high. Let's watch. It didn't even get to the 8-second mark, but at 6 seconds, it is past the 119 it was at 8 seconds. So this graph shows that the height increased more steeply because the cart sped up more quickly. Give you a second to check your answer there. I already showed you what that looks like, so the answer to what do you observe is that the graph goes up more steeply and the finishing time is less. I'm going to give you a minute or two to read question 8. So this one you were supposed to design an experiment to test the effect of force on a loaded cart. So we have not yet loaded the cart. So you will need to decide whether you're in high, low, or medium, and what kind of loaded cart you have. when you add the mass there. Can't drag it at the moment. There we go. So it's up to you to decide what that experiment looks like. I'll give you about 2 minutes to read through those components that you needed to have. Okay, moving on. Activity B, running out of steam. You're going to click reset. I'm going to need to put my objects back. You're going to set the ground or the friction tape to metal. And then you will begin activity B. We're going to look at this question. Why do objects slow down when nothing pushes them? So you're going to try different objects and different surfaces, and then turn the fan force to off if a cart is moving. You then need to form a hypothesis of what causes the object to slow down after it is no longer being pushed. Here, your answers may vary, which is part of the reason in science, everyone. I'm telling you all the time, I'm looking for an answer, not the answer. So the hypothesis you made, you likely got this question correct because it can be any number of things. Okay, there's not one correct answer here. I'm not looking for one thing. That's kind of the case for all of activity B. So depending on what you picked and what your answer is if it is a correct answer or not. So that takes you or I looking at it to see if those hypotheses and predictions match up based on the experiment you were running, because every single person is going to test and run a different trial. But the conclusion you do need to come to is that friction causes objects to slow down. And if there were no friction, if we lived in a world with no friction, the cart would never slow down because there are no forces acting upon it. That means it would never stop in that perfect orb vacuum of a world if there was no friction, no other forces. Which surface had the most friction in Gizmos? The answer is wood. Activity C. You're seeing here with no friction, as well as soda and a book, and the fan force set to high. Kind of slow even with a high fan force when it's a weighted cart. We didn't even get to the hundreds there. 89.5. So once you run that experiment, you're going to come in here and answer these questions. Oh, I didn't read that first part. We're going to run it again and stop it at 3 seconds. I skipped it. 1, 2, 3. I'm skipping it a little bit, not quite there, but around 31. Okay. Select the Data tab. Select Position. The position of the cart is on location. How far from the start line? What pattern do you see in this data? So what we are seeing in this data is that for every 3 seconds, the cart's going to move nearly 50 centimeters in that 3 seconds. The answer I have here in the data tab is exactly, they have it as 32 centimeters greater than the previous one for each second. So that means they were looking at it exactly. I think there's going to be variation between all our experiments, so as long as you're in the range there and you looked at the graph. I'm not looking for this exact answer, I promise you. I'm kind of just looking for this whole explanation of that you have a full sentence or two, capitalization, punctuation, and that you answered something in terms of the data chart and looking at the position. I'll give you another minute here to read the ending questions because, again, it's going to depend on your settings of your simulation. But as long as you have something in this ballpark where you talk about similar things, you would get that part of the lab correct.